In trigonometry, we relate the sides of a triangle to the interior angles of a triangle. First, we'll start looking at right-angled triangles, and we know with a right-angled triangle we have a hypotenuse, which is the longest side in our right-angled triangle, and it's also opposite our right angle. The other two shorter sides we identify relative to another interior angle. Most commonly, we refer to an angle using the symbol theta. So the other two sides we identify as being opposite this angle theta or adjacent the angle. When referring to these sides, we'll commonly just use the first letter. You may recall with right-angled triangles we have Pythagoras' theorem, which relates the length of the three sides of our right-angled triangle together. In this relationship, where C is the hypotenuse and A and B are the two shorter sides of our triangle, we'll use this commonly in application-style questions later in the unit. There are three trig ratios that apply for right-angled triangles. First, we have sine theta, which equals the ratio of the opposite side on the hypotenuse. So what this equation is saying is that if we know the angle theta, then for that right-angled triangle, the ratio of the opposite side to the hypotenuse is always the same value. And sine theta is simply a function which we sub in a value of theta, and it tells us what the ratio's value is. And we know that we're just going to be using the magic of our calculator to get that value. Next we have cos theta, which is the adjacent side divided by the hypotenuse, and tan theta, which is the opposite side divided by the adjacent. Now if we look back at sine theta, the ratio that we get from this function must always be less than 1, and that's because the hypotenuse must be the longest side of our triangle. I can write that mathematically by saying the value of sine theta, the ratio, must be between 0 and 1. The same applies for cos theta, but the only restriction for tan theta is that it must be greater than 0. And we can see why, because we can get a ratio bigger than 1 here if the opposite side is longer than the adjacent, which is perfectly possible. Now let's look at how we use those three functions to solve for an unknown side in a right-angled triangle. So in this example, we're given an angle of 25 degrees, a hypotenuse of 18, and an unknown x. The first step to solving is to label the known quantities. The hypotenuse is easy to identify. We have our angle theta of 25 degrees, and x is opposite our angle. So writing those down for good communication. Next we need to figure out which trig ratio relates the opposite side to the hypotenuse. And of course that's sine theta. So now we substitute in, and now we just have an equation to solve. If you go to your calculator and you could punch in sine 25 degrees, and you'll find it's a non-recurring decimal. So we don't want to do that just yet because it won't be very nice communication. So we see that x is being divided by 18. So to get x by itself, or to solve for x, we need to times both sides by 18. And we get an answer of 7.6. But it's important to realise this is not the exact answer, it's just approximate. So we communicate that by saying our answer is correct to one decimal place only. Here's another example that will use a different trig ratio using the same angle. So first we'll label. Start with identifying the hypotenuse. Here the question won't involve the hypotenuse, so we'll continue labelling and writing down what we know. Now we have to identify the correct trig ratio. which this time is tan theta, and then substitute in. Here we see our unknown value is on the denominator of the ratio, so to solve this time the process is a little bit different. The first thing I'll do is multiply both sides by x, and then I'll divide through by tan 25 degrees, remembering that this is just a number. And we get x equals 19.3. We should do a quick check here to see if our answer is reasonable, and yes, we were expecting this side here to be bigger than 9, which is consistent with our answer. Next, let's look at solving for an unknown angle. So on this right angle triangle, we know two sides. So we could use Pythagoras to find the length of the third side. So there's only one possible triangle we can make here, which means there should be a way of figuring out what this angle theta is. Now write down what we know and identify the trig ratio we need to use. So it's sine theta this time. So now substitute in. Now this equation is very different. So we want to solve for the angle theta, but it's part of this sine theta function. So in this problem, we actually know the ratio of the opposite side to the hypotenuse. It's exactly 27 on 34. So what we're after is, well, what angle do we take the sine of to give that ratio? So we're going to have to ask our calculators that question. And this is the first time in mathematics where you see some strange notation, and the notation is sine to the minus 1. Now this can be a little bit confusing because you've seen the minus 1 before in your index rules, but this is completely different. The role of sine to the minus 1 is to essentially go backwards here, or undo what sine does. So when we have an angle theta, we can take the sine of that angle theta, and that gives us the sine ratio. If we know the ratio, then we can take sine to the minus 1 of the ratio, and that will tell us the angle. So here, what we're going to do to solve for theta is to apply the sine to the minus 1 function to both sides of our equal sign. Because remember, when we're solving an equation, we must do the same thing to both sides. So now on the left-hand side, we have sine to the minus 1 of sine of theta. But sine to the minus 1 and sine do opposite things. They're like squaring, then taking the square root, or adding 1 and then taking 1. They simply cancel each other out. So on the left-hand side, we simply have theta. On the right-hand side, sine to the minus 1 of our ratio, 27 on 34. So in your working out, you would not show this middle line here. You'll go down to from sine theta equals to the angle theta equals the inverse sine, sine to the minus 1, of the ratio. And if you do that, you get an answer of 52.6 degrees. To do this on your calculator, you'll need to use the inverse sine seen here above the sine function. So you'll need to press Shift Sine to bring up the inverse sine, and then type in your ratio, 27 on 34. And that should give you the answer of 52.6 degrees.